Welcome to Nebula Nights. Tonight we're taking a look at one of humanity's greatest achievements in space exploration, the Voyager missions. But before we can understand why Voyager became so important, we have to go back, long before rockets, satellites, or even airplanes. For as long as humans have existed, we've looked up at the night sky and wondered what was out there. Those tiny points of light inspired myths, guided sailors across oceans, and eventually pushed us to ask questions that would shape science itself. For centuries, the stars remained just that, distant lights, beautiful to look at, impossible to reach. But little by little, that began to change. The work of astronomers, mathematicians, physicists, and engineers slowly transformed our understanding of the universe. We learned that the Earth wasn't the center of everything. We discovered the laws that govern the motion of planets. Eventually, we learned not just how to understand gravity, but how to fight against it. In 1957, humanity crossed an invisible line for the very first time when the Soviet Union launched Sputnik 1, the world's first artificial satellite. It was a simple metal sphere, but it marked the beginning of the space age. From there, progress came surprisingly quickly. Just 12 years later, humans were walking on the moon. Robotic spacecraft began visiting our neighboring planets, sending back images that no one had ever seen before. One of my personal favorites is the Soviet Venera program. Somehow, engineers managed to build spacecraft capable of surviving the crushing pressure and extreme temperatures on the surface of Venus long enough to send back photographs. Honestly, it's one of the most impressive engineering achievements in space exploration, and it absolutely deserves its own episode someday. But even after reaching the moon and exploring the inner planets, one question remained. How far could we really go? Could we build a spacecraft capable of visiting the giant planets? Could we build one that would leave the solar system altogether? As it turned out, timing couldn't have been better. In the 1960s, scientists realized that the outer planets were approaching a rare alignment, one that would make a mission previously thought impossible suddenly achievable. And that discovery would eventually become the Voyager program. Before NASA could build Voyager, they first had to answer a much simpler question. How do you actually get there? Reaching the outer planets isn't just a matter of building a bigger rocket and pointing it in the right direction. Space is unimaginably vast, and every extra kilometer per second of speed requires more fuel. The problem is that fuel is heavy. The more fuel you bring, the heavier your spacecraft becomes, but a heavier spacecraft needs an even bigger rocket to launch it. And that bigger rocket also needs more fuel. It's a problem that quickly starts working against itself. By the early 1960s, scientists were eager to explore Jupiter and Saturn, but Uranus and Neptune seemed almost out of reach. The rockets of the time simply couldn't send a large scientific spacecraft that far without some clever solution. That solution would come from mathematics. In 1964, a young engineer at NASA's Jet Propulsion Laboratory named Gary Flandreau was studying possible flight paths to the outer planets. His job wasn't to invent a new spacecraft or a more powerful rocket. He was simply looking for the most efficient routes through the solar system. While running those calculations, he noticed something remarkable. During the late 1970s, the four giant planets, Jupiter, Saturn, Uranus, and Neptune, would be positioned in a way that hadn't happened for generations. They wouldn't form a perfect straight line, like they're often shown in illustrations, but they would be close enough that a spacecraft could travel from one planet to the next using gravity itself as a source of acceleration. This technique is called a gravity assist, or sometimes a gravitational slingshot, and I honestly think it's one of the cleverest ideas in the history of space exploration. At first, it almost sounds like magic. A spacecraft flies toward a planet, swings around it, and somehow leaves moving faster than it arrived. So, where does that extra speed come from? The answer is the planet itself. Every planet is constantly moving around the Sun at incredible speed. Jupiter, for example, travels at roughly 13 kilometers every single second. When a spacecraft approaches from just the right angle, it can borrow a tiny amount of that enormous orbital energy. The spacecraft gains speed, while Jupiter loses an amount of energy so incredibly small that it's effectively impossible to notice. So yes, technically, Voyager slowed Jupiter down, just by an amount so unimaginably tiny that the planet will never notice. It's one of those facts that sounds made up, but it's completely true. Without gravity assists, missions to the outer planets would have required far larger rockets, much more fuel, or entirely different mission designs. Instead of letting chemistry do all the work, engineers found a way to let the solar system help. And the timing couldn't have been better. This particular alignment of the outer planets only happens about once every 76 years. The previous opportunity came long before anyone had even dreamed of spaceflight, and the next one won't arrive until well into the 22nd century. It was, quite literally, a once-in-a-lifetime opportunity. NASA quickly realized what this meant. Instead of sending separate spacecraft to each of the giant planets, it might be possible to visit several of them with a single mission. The original proposal became known as the Grand Tour, an ambitious plan that would explore the outer solar system in a way that had never been attempted before. The mission looked incredible on paper. Unfortunately, it also looked incredibly expensive. As the Apollo program came to an end and NASA's budget began to shrink, the Grand Tour was eventually cancelled before a single spacecraft could be built. For a moment, it looked as if this rare opportunity would simply pass by, but NASA wasn't ready to give up. Instead of abandoning the idea completely, engineers went back to the drawing board. They asked themselves a new question. What is the greatest mission we can build with the budget we actually have? The answer wouldn't be called the Grand Tour. It would be called Voyager. With the mission finally taking shape, NASA now faced an entirely different challenge. They knew where they wanted to go. Now they had to build a spacecraft capable of surviving one of the longest and most unforgiving journeys ever attempted. Unlike a satellite orbiting Earth, Voyager would travel farther than any spacecraft before it. There would be no servicing missions, no replacement parts, and no astronauts waiting to repair it if something went wrong. Once Voyager left Earth, whatever engineers had built would have to work on its own. Every decision suddenly mattered. One of the very first problems was power. Today, when we think of spacecraft, we usually picture large solar panels unfolding toward the sun. Around Earth, that's a fantastic solution. Sunlight is plentiful, and modern solar panels can generate electricity for many years. But Voyager wasn't going to stay anywhere near Earth. The farther you travel from the sun, the weaker its light becomes. By the time you reach Jupiter, sunlight is already only a small fraction of what we receive here on Earth. By Neptune, it's roughly 900 times weaker. Solar panels large enough to power Voyager simply weren't practical with the launch vehicles available in the 1970s. NASA needed another solution. The answer came in the form of something called a radioisotope thermoelectric generator, or RTG for short. It sounds incredibly complicated, but the idea is actually beautifully simple. Inside each RTG is a small pellet of plutonium. As the plutonium naturally decays, it continuously gives off heat. That heat passes through devices called thermocouples, which convert the temperature difference directly into electricity. There are no moving parts, no turbines, no combustion, no tiny nuclear reactor hidden inside the spacecraft. Just physics quietly doing its job day after day, year after year. Even today, nearly 50 years after launch, those generators are still producing electricity, although a little less each year. That's one of the reasons NASA has gradually had to switch off scientific instruments, to make sure the remaining power goes to the systems keeping Voyager alive. But generating electricity was only part of the challenge. Voyager also had to know where it was pointing. Once the planetary flybys were complete, there would be no engines pushing the spacecraft forward. In fact, that's one of the fascinating things about traveling through space. According to Newton's first law, once an object is moving, it will continue moving unless another force acts on it. Voyager doesn't need engines to keep traveling through interstellar space. It already has all the speed it needs. Instead, its engines have a much more delicate job. They keep the spacecraft pointed toward Earth. Every photograph, every scientific measurement, and every tiny stream of data must be transmitted through Voyager's large white high-gain antenna. If that antenna drifts even slightly away from Earth, communication eventually becomes impossible. To prevent that, Voyager uses 16 tiny hydrazine thrusters positioned around the spacecraft. Their operation is surprisingly elegant. Hydrazine is stored as a liquid inside pressurized fuel tanks. When Voyager needs to rotate, a valve opens for just a fraction of a second, allowing a tiny amount of hydrazine to flow into a small chamber containing a catalyst. The moment the hydrazine touches that catalyst, it rapidly decomposes into extremely hot gases. Those gases expand and rush out through a nozzle at tremendous speed. That's the rocket engine. No spark plugs, no flame, no moving pistons, just chemistry. Each burst lasts only milliseconds, producing a surprisingly small amount of thrust. But in the frictionless vacuum of space, that's all Voyager needs to gently rotate itself. It's amazing to think that some of those tiny thrusters have now fired hundreds of thousands of times over nearly half a century, and they're still working. Then there was the spacecraft's brain. Compared to today's computers, Voyager's onboard systems are unbelievably modest. A modern smartphone has millions of times more processing power, yet Voyager continues to navigate interstellar space with hardware designed in the early 1970s. Rather than relying on one central computer, Voyager actually carries several specialized computers. One controls the spacecraft's orientation, another receives and interprets commands from Earth, while another manages the scientific instruments and the data they collect. Each system has a specific responsibility, making the spacecraft far more reliable than if everything depended on a single computer. What's perhaps even more remarkable is how those computers are programmed. Engineers don't connect remotely and control Voyager like you might control a rover with a joystick. Instead, they write carefully planned command sequences here on Earth. Those commands are tested extensively before being transmitted through NASA's Deep Space Network. Today, because Voyager is so far away, a single command takes well over 20 hours just to reach the spacecraft. If engineers want to see whether it worked, they have to wait another 20 hours or more for the reply. Imagine trying to repair your computer. Every click of the mouse takes almost 2 days to confirm. And here's something I think is absolutely incredible. Voyager's software is written in assembly language for custom-built computers that exist nowhere else. Many of the engineers who originally designed those systems retired decades ago. In recent years, when Voyager began experiencing memory faults billions of kilometers from Earth, modern engineers had to study those original documents, understand computers built in another era, and then write new assembly code to work around damaged memory. They couldn't replace the faulty hardware. Instead, they taught a 47-year-old spacecraft to use different parts of its own memory, all from Earth, over 24 billion kilometers away. I don't know about you, but I think that's one of the greatest feats of engineering and problem-solving in the history of space exploration, because Voyager wasn't simply built to explore the solar system. It was built so well that half a century later, humanity is still finding ways to keep it alive. By now, Voyager had become much more than just another spacecraft. It was about to travel farther than anything humanity had ever built. And for the very first time, someone asked a question that had never really been asked before. If this spacecraft survives long enough to be found, what should it say about us? I absolutely love this question, because there isn't a correct answer. How do you summarize humanity? Do you talk about science, music, art, religion, mathematics, love? There simply isn't enough room to include everything. In 1977, NASA asked astronomer Carl Sagan to lead a small team that would answer exactly that question. They didn't have years to work on it. In fact, they only had a matter of weeks before Voyager was due to launch. No pressure, right? The team's solution became known as the Golden Record. If you've never seen one before, it looks surprisingly familiar. It's essentially a phonograph record, very similar to a vinyl record you might have at home. And yes, that immediately raises another question. Why a record? Why not a cassette tape? Or a CD? Or, if we were doing this today, maybe even a USB stick? The answer is actually quite clever. A record doesn't rely on any particular computer system or software. If another civilization understands physics well enough to find Voyager, there's at least a chance they'll also figure out how a groove carved into a disk stores information. NASA even included a stylus and engraved simple playback instructions directly onto the protective cover. The whole thing was designed to explain itself, which I think is brilliant. The record itself is made from copper and coated in gold, not because gold looks impressive, but because it resists corrosion incredibly well. The hope was simple. If Voyager drifted through interstellar space for millions of years, the record might still be there. Long after every person alive today is gone, long after our cities have disappeared, that little gold record may still be quietly traveling between the stars. Then came the impossible part, deciding what to put on it. The final record contains greetings in 55 different languages, sounds from the nature, music from cultures around the world. Even Chuck Berry somehow made the cut, which means there's a very real possibility that the first human song an alien civilization hears is Johnny B. Good. That would be cool. But I think the most beautiful thing on the record isn't the music, it's the idea behind it. Nobody expected aliens to find Voyager. The chances are unbelievably small. This wasn't really a message sent because we expected a reply. It was a message sent because, for the first time in history, humanity had the ability to introduce itself to the universe. And we decided it was worth saying, hello. By the summer of 1977, years of planning, engineering, and testing had all led to one moment: launch day. Everything that could be tested had been tested. Every instrument had been checked. Every wire had been inspected. Soon there would be no more opportunities to fix anything. Once Voyager left the launch pad, the spacecraft would be on its own. I sometimes wonder what that must have felt like for the engineers. Imagine spending years designing something, solving hundreds of problems, testing every possible failure you can think of. Then, one morning, you simply have to trust that you got it right. Voyager would leave our planet aboard one of the most powerful rockets available at the time, the Titan IIIe rocket. Compared to the spacecraft it carried, the rocket looked absolutely enormous. Voyager itself weighed less than a family car. The rocket carrying it into space stood almost 50 meters tall. It's a good reminder that getting into space is often much harder than traveling once you're already there. The rocket's job was only the beginning. It had to lift Voyager above the atmosphere and give it enough speed to escape our planet's gravity. After that, physics would take over. One thing that often confuses people is the order of the launches. Voyager 2 actually launched first on the 20th of August 1977. Voyager 1 followed just 16 days later. That sounds backwards, and honestly, it kind of is. The reason is actually pretty clever. Voyager 2 had the longer journey. Its planned route would eventually take it past Uranus and Neptune, meaning it needed an earlier start. Voyager 1, on the other hand, followed a faster trajectory toward Jupiter and Saturn. Even though it launched later, it arrived first. That's one of my favorite little Voyager facts. Another thing I think is easy to forget is that rockets don't simply point toward Jupiter and fly there. Jupiter is moving. Our own planet is moving. Every planet in the solar system is constantly traveling around the sun. Mission planners therefore had to calculate where Jupiter would be months later, not where it happened to be on launch day. Miss that target by even a tiny amount and the entire gravity assist sequence could be lost. It's a little like throwing a ball to someone who's running across a football field. You don't throw the ball where they are. You throw it where they'll be when the ball arrives. Except in Voyager's case, the throw lasted for months. I think that's a pretty crazy thing to think about. As the Titan IIIe disappeared into the Florida sky, humanity started something completely new. We weren't simply sending another spacecraft to visit another planet. We were sending a machine that, if everything worked exactly as planned, would eventually leave the solar system forever. But before Voyager could begin that lonely journey between the stars, it first had to survive an encounter with the largest planet in our solar system. And, as it turned out, Jupiter had a few surprises waiting. Because after months traveling through space, Voyager finally reached its first destination, Jupiter. Even today, it's difficult to appreciate just how exciting that moment was. Up until then, Jupiter had always been observed from a distance. Powerful telescopes had revealed its colorful cloud bands and its famous Great Red Spot, but nobody had ever seen the planet the way Voyager was about to. For the first time, humanity wasn't simply looking at Jupiter. We were paying it a visit. As Voyager closed in, it began returning photographs unlike anything seen before. The amount of detail was astonishing. Storm systems stretched across thousands of kilometers. Clouds twisted around one another in beautiful patterns. The Great Red Spot turned out to be even more spectacular than scientists had imagined. It's a storm so large that the entire Earth could fit inside it. And what's even more incredible is that we've watched it rage for centuries. It's still there today, still spinning, still refusing to disappear. But I actually don't think Jupiter itself was Voyager's greatest discovery. I think that honor belongs to one of its moons, Io. Before Voyager arrived, scientists assumed moons were fairly quiet places. Cold, old, geologically inactive. Io had other ideas. Voyager photographed giant plumes rising hundreds of kilometers above the surface. At first, nobody quite knew what they were looking at. Then the realization hit. They weren't mountains. They weren't clouds. They were volcanoes. Active volcanoes. The first ever discovered anywhere beyond our own planet. That completely changed planetary science. The obvious question became, why? The answer comes down to gravity. Every time Io orbits Jupiter, the giant planet's enormous gravity stretches and squeezes the moon ever so slightly. Europa and Ganymede tug on it as well, making the effect even stronger. Imagine bending a paperclip back and forth over and over again. It gets warm, keep going, and eventually it becomes hot. Something very similar happens to Io, except instead of heating a paperclip, gravity is heating an entire moon. Deep beneath the surface, rock melts, pressure builds. Volcanoes erupt. I think that's incredible. A moon powered by gravity. Voyager didn't stop there. It also discovered that Jupiter has a faint ring system, something many people still don't know today because Saturn's spectacular rings tend to steal all the attention. It also revealed Europa's cracked, icy surface and helped us understand that Ganymede is actually larger than the planet Mercury. Every flyby seemed to answer one question while creating 10 more. And that's probably my favorite thing about exploration. Every discovery reminds us how much we still don't know, but Voyager's journey was only just beginning. Waiting ahead was perhaps the most beautiful planet in the entire solar system, Saturn. By the time Voyager reached Saturn, the mission had already been an incredible success. Jupiter had exceeded every expectation. The spacecraft was healthy, and scientists were now preparing for what many considered the second great prize of the mission. Saturn itself was breathtaking. Even today, I think it's probably the planet most people imagine when they picture our solar system. Those enormous rings almost look artificial, as if someone deliberately placed them there just to make Saturn stand out from the rest of the planets. But as beautiful as Saturn is, that's actually not the most important part of this chapter. Because this is where the story of Voyager changes. Up until now, we've mostly talked about Voyager as if it were a single spacecraft, but in reality, there were always two. Voyager 1 and Voyager 2 were built almost identically, launched only 16 days apart, and worked together as a team. Even though they followed different trajectories, they were really two halves of the same mission. NASA didn't build two spacecraft simply because they expected one to fail. Having two Voyagers allowed them to attempt something much more ambitious than a single spacecraft ever could. If everything went according to plan, both would visit Jupiter and Saturn, but after that their paths would separate forever. That separation had already been decided before either spacecraft ever left the launch pad. Voyager 1 was given the faster trajectory because it had one very specific scientific objective: Titan. Titan is Saturn's largest moon, and even before the mission launched, scientists knew it was unlike anything else in the solar system. It has a thick atmosphere, thicker even than the atmosphere on our own planet, and many researchers suspected it might hold clues about what the early Earth looked like billions of years ago. If Voyager was going to answer those questions, it had to pass extremely close to Titan. But there was a catch. Spacecraft don't simply fly past planets and moons without consequence. Every close encounter changes their trajectory, and the closer Voyager 1 passed Titan, the more Saturn's gravity would bend its path. That flyby would send the spacecraft upward, out of the relatively flat plane where the planets orbit the Sun. Once that happened, there was no coming back. No Uranus. No Neptune. No second chance. It sounds dramatic, but this wasn't an accident or a mistake. It was one of the most carefully considered decisions of the entire Voyager program. NASA concluded that studying Titan up close would teach us more than sending Voyager 1 onward to the remaining outer planets. In other words, the mission wasn't ending early. It was doing exactly what it had been designed to do. And that's where Voyager 2 enters the story. While Voyager 1 turned toward Titan and then began climbing out of the planetary plane, Voyager 2 quietly continued along the original Grand Tour trajectory. From that moment on, it became humanity's only opportunity to visit Uranus and Neptune, and the success of the entire extended mission now depended on a single spacecraft staying healthy for another 8 years. That's actually a crazy thought when you stop and think about it. Everything we know from the first and only close-up visits to Uranus and Neptune depended on one machine surviving a journey that nobody had ever attempted before. Looking back today, it's easy to think of Voyager 1 and Voyager 2 as separate missions because that's how we usually talk about them. But standing there in 1980, watching Voyager 1 leave Saturn behind, they were still part of the same story. One spacecraft had completed the mission it was built to fly, the other was about to continue into completely unexplored territory. Waiting ahead for Voyager 2 was a planet no spacecraft had ever seen up close, Uranus. As Voyager 2 left Neptune behind, something quietly came to an end. Since the launch of Sputnik in 1957, humanity had been steadily expanding its reach into the solar system, first with satellites, then the moon, then the inner planets, and finally the gas giants. Each mission had pushed the frontier a little farther from the Sun, but now, for the first time, there were simply no more planets waiting ahead. I think that's a surprisingly strange thought. For more than 30 years, every major space mission had another destination waiting somewhere out there. Voyager 2 was different. Once Neptune disappeared behind it, there was no next planet to prepare for, no upcoming flyby, and no new world waiting around the corner. The spacecraft had reached the end of what we usually think of as the solar system. But before we leave Neptune completely, I think it's worth taking a moment to appreciate just how extraordinary this encounter really was. Voyager 2 arrived in 1989 after traveling for 12 years, becoming the first spacecraft ever to visit Neptune and, more importantly, the only one that has done so ever since. Every close-up image you've ever seen of Neptune comes from those few precious hours, and every detailed photograph of Triton, its largest moon, comes from that same flyby. That's actually incredible when you stop and think about it. We often imagine space exploration as something that's constantly moving forward. But there are entire planets where almost everything we know still comes from a single spacecraft that visited once and then continued on its way. Neptune itself turned out to be far more active than anyone expected. Scientists discovered enormous storms moving through its atmosphere and measured winds reaching well over 2,000 kilometers per hour, making them the fastest winds ever recorded on any planet in the solar system. That's particularly surprising because Neptune receives only a tiny fraction of the sunlight that reaches us, proving that the energy driving a planet's weather doesn't always come directly from the sun. Then there was Triton. If you've paid attention, you've probably noticed a pattern by now. Every time Voyager visited a completely new world, it found something scientists weren't expecting, and Triton was no exception. Instead of being an old frozen moon that had been geologically inactive for billions of years, Voyager photographed giant plumes erupting from its surface. They looked almost like volcanic eruptions, except they weren't driven by molten rock. Instead, they were powered by frozen materials such as nitrogen that turned directly into gas beneath the surface before bursting upward through the ice. I have to admit, I love discoveries like that because they remind us how dangerous assumptions can be. If we had judged Triton simply because it was cold, we would probably have assumed nothing interesting could still be happening there. Nature clearly had other ideas. By the time Voyager 2 completed its flyby, the original Grand Tour had finally come to an end. 25 years earlier, Gary Flandreau had noticed a rare alignment of the outer planets that only happens about once every 176 years. However, that discovery eventually became the Voyager program, and now, after more than a decade of exploration, humanity had successfully visited Jupiter, Saturn, Uranus, and Neptune during a single mission. Looking back today, it's difficult to appreciate just how ambitious that must have sounded in the 1960s. At the time, nobody knew whether the spacecraft would survive Jupiter's radiation belts, whether the computers would still be working years later, or whether the tiny hydrazine thrusters would still be able to keep the antenna pointed toward home after traveling billions of kilometers through space. Somehow, they all did. The engineering worked. The mathematics worked. The mission worked. But perhaps the strangest part of the story was that Voyager wasn't finished yet. The planets were now behind both spacecraft, but they were still moving, still transmitting, and still heading toward a place no human-made object had ever reached before, the edge of the sun's influence. And beyond that, the space between the stars. By the time Voyager 2 left Neptune behind, the mission had achieved something no one had ever done before. Humanity had explored all 4 giant planets in a single program, and for the first time there were no more planetary flybys waiting ahead. There is, however, one question that almost always comes up whenever people talk about Voyager. What about Pluto? After all, Pluto was still considered the 9th planet when Voyager launched, so why didn't either spacecraft visit it? The answer comes down to trajectory. Voyager wasn't designed to visit every planet. It was designed to take advantage of a very specific alignment of the outer solar system, using gravity assists to build speed from one planet to the next. Pluto simply wasn't in the right place to be included without giving up the rest of the mission. Once NASA decided that Voyager 1 would fly close to Titan, its path out of the solar system was fixed. Voyager 2, meanwhile, continued toward Uranus and Neptune. There simply wasn't a route that allowed either spacecraft to do everything. Looking back today, I actually think NASA made the right choice. Thanks to Voyager, we became the first generation to see Uranus and Neptune up close, and more than 30 years later they're still the only close-up views we've ever had. Pluto eventually got its own mission when New Horizons flew past in 2015, revealing a surprisingly beautiful and complex world. By then, Pluto had already been reclassified as a dwarf planet, which makes the whole story a little ironic. Voyager never visited what used to be the 9th planet, while the spacecraft that finally did arrived after Pluto had lost that title. With the planets now behind them, both Voyager spacecraft entered a completely different phase of their lives. One thing I used to wonder about was what it actually means to leave the solar system. Is there some invisible border where you're suddenly outside? Does the sun simply stop pulling on you? The answer is actually much more interesting than that. Even where Voyager is today, the sun's gravity is still there and always will be. Unless another passing star disturbs their paths millions of years from now, both spacecraft will continue orbiting the center of the Milky Way together with our sun. So when people say that Voyager has left the solar system, they aren't talking about gravity. They're talking about the sun's influence. Our sun constantly releases a stream of electrically charged particles called the solar wind. That wind expands outward in every direction, creating an enormous bubble around our planetary system known as the heliosphere. You can think of it as a giant protective bubble that shields the planets from much of the radiation that exists between the stars. As Voyager traveled farther and farther away, that solar wind gradually weakened until it finally met the thin gas already filling interstellar space. The place where those two pressures balance each other is called the heliopause, and crossing that boundary means leaving the sun's protective bubble behind. Voyager 1 crossed the heliopause in 2012, becoming the first human-made object ever to enter interstellar space. Voyager 2 followed in 2018, giving scientists a second set of measurements from a completely different region of the heliosphere. Having 2 spacecraft once again proved incredibly valuable, because nature rarely behaves exactly the same in every direction. By this point, the mission had quietly transformed into something completely new. Voyager was no longer exploring planets. It was exploring the space between the stars. Every signal arriving at the Deep Space Network now carries information from an environment no human-made instrument had ever sampled before. Those signals are unimaginably weak after traveling for more than 20 hours across billions of kilometers, yet engineers are still able to detect them and continue a conversation that began almost half a century ago. I think that's an amazing thought. These spacecraft were built to explore the outer planets, but they ended up becoming humanity's very first interstellar explorers. And somehow, they're still not finished. Because keeping Voyager alive today has become a remarkable engineering story all by itself. By now, Voyager has traveled farther than anyone involved with the original mission ever expected. What began as a journey to explore the outer planets has become humanity's longest-running space mission, and even today the spacecraft continues to send back data from a place no human being has ever visited. But keeping Voyager alive has quietly become one of the most remarkable engineering stories in the history of space exploration. Every year, the spacecraft produces a little less electrical power than it did the year before. The radioisotope generators that have faithfully powered Voyager since 1977 continue to lose output as the plutonium inside them slowly decays. There's nothing anyone can do to stop it. Because of that, NASA has spent years making difficult decisions about which systems should remain powered and which ones must be switched off forever. Every instrument that goes silent extends the mission just a little longer, allowing Voyager to continue sending back information from interstellar space. In a way, it's a little like trying to keep an old lighthouse shining by turning off one light after another, hoping the most important beacon can stay on just a little while longer. And then, just when you might think the mission had settled into a quiet routine, something unexpected happened. In late 2023, Voyager 1 began sending data that no longer made any sense. The spacecraft was still responding to commands, but the information reaching Earth looked like complete gibberish. Imagine receiving a phone call from someone you know, hearing their voice, but every sentence comes out as nonsense. You know they're still there. You just can't understand what they're trying to tell you. That was the situation NASA suddenly found itself in. The problem wasn't simply that Voyager was old. The spacecraft was now more than 24 billion kilometers away, traveling through interstellar space, with every command taking well over 20 hours to arrive, and every reply taking just as long to return. Every attempt to solve the problem took almost 2 full days before engineers knew whether it had worked. After months of investigation, the team traced the fault to damaged memory inside one of Voyager's onboard computers. They couldn't replace the hardware, and they certainly couldn't send a repair mission. So they did something I still find hard to believe. They went back to thousands of pages of engineering documents written in the 1970s, studied computer systems that almost nobody works with anymore, wrote new assembly code, and carefully moved parts of Voyager's software into healthy sections of memory that had never originally been intended for that purpose. In other words, they performed brain surgery on a spacecraft drifting through the space between the stars, from Earth, and somehow, it worked. Voyager began speaking clearly again. I think that's one of those moments that perfectly captures what this mission has always been about. Not just building extraordinary machines, but building teams of people willing to solve problems that nobody has ever faced before. Even after crossing into interstellar space, Voyager continues to surprise us. Its instruments have detected faint plasma waves drifting through the gas between the stars, allowing scientists to study an environment that was completely beyond our reach before these spacecraft arrived there. Every new measurement reminds us that exploration doesn't always end when the photographs stop. Sometimes, the most important discoveries begin only after you've reached the place nobody expected you to survive. Eventually, the day will come when Voyager's power finally runs out. One by one, the remaining instruments will fall silent until there isn't enough electricity left to power the transmitter. There won't be a dramatic explosion or a final farewell. One day, it will simply stop answering. After that, both Voyager spacecraft will continue their journey exactly as they always have, silently orbiting the center of the Milky Way alongside our Sun. In tens of thousands of years, they'll pass relatively close to other stars, and for hundreds of millions of years they'll continue drifting through our galaxy, carrying the golden records that Carl Sagan and his team prepared all those years ago. Will anyone ever find them? Honestly, we have no idea. Maybe the records will never be played. Maybe no other civilization will ever know they exist, but strangely enough, I don't think that's the point. The golden record was never really about expecting an answer. It was about saying something. It was humanity's way of introducing itself to a universe we barely understood. Not because we thought someone was listening, but because curiosity has always been one of the defining traits of our species. I think that's why the Voyager program has remained so special for nearly 50 years. It isn't just a story about spacecraft. It isn't just a story about engineering. It isn't even just a story about space. It's a story about what happens when ordinary people become curious enough to ask questions that seem impossible to answer. Questions like, can we reach the outer planets? Can we leave the solar system? Can we build something that outlives us? The answer to every one of those questions turned out to be yes. And somewhere, unbelievably far from home, two small spacecraft are still carrying that answer with them as they quietly disappear into the darkness between the stars. Thank you so much for joining me tonight on Nebula Nights. I'll see you in the next one.